In the soft glow of a Copenhagen morning, on October 7, 1885, a child was born who would one day change the way humanity understood the universe. His name was Niels Henrik David Bohr. The city around him was peaceful, its cobblestone streets echoing with the steady rhythm of horse carriages and the distant calls of merchants by the harbor. Copenhagen was a city of quiet charm and intellectual vigor, a place where art, science, and philosophy found a shared home. It was in this environment that Bohr's remarkable journey began, not with the flash of genius that would later define him, but with the nurturing of a family steeped in curiosity, conversation, and the pursuit of truth. Niels was born into a family that valued knowledge as much as warmth. His father, Christian Bohr, was a professor of physiology at the University of Copenhagen, a man whose fascination with life's hidden processes made him a pioneering figure in his field. Christian was known not only for his scientific achievements, but for his ability to turn complex ideas into everyday conversations at the family dinner table. He often spoke of the mysteries of the human body, the way blood carried oxygen, the interplay between heart and brain, topics that fascinated the young Niels, even if he did not yet understand their depth. His mother, Ellen Adler Bohr, came from a prominent Jewish family known for their contributions to education and politics. She possessed a quiet strength, a balance of intellect and compassion that would deeply influence her children. Together, Christian and Ellen created a home where ideas were not just discussed but celebrated. The Bohr household was one of constant learning. Books lined the shelves of every room, and lively debates filled the evenings. Visitors from the university often joined the family for dinner. Scientists, philosophers, and students who would share their thoughts and discoveries, unaware that the curious young boy listening intently would one day surpass them all. From an early age, Niels displayed an exceptional ability to observe and question. He was not content to accept things at face value. When others saw simplicity, Niels saw complexity. When others found answers, he found new questions. Niels had an older brother, Harold, who would also become a brilliant mind, a mathematician and footballer who represented Denmark in the 1908 Olympic Games. The brothers shared a deep bond, one built on mutual respect and intellectual playfulness. They would spend hours discussing mathematics, experimenting with homemade instruments, or conducting small physics tests in their home laboratory, a makeshift corner of their father's study where curiosity reigned supreme. While Harold's mind was sharp and systematic, Niels's was intuitive and creative. He saw patterns in chaos and meaning in mystery, qualities that would later define his unique approach to physics. At school, Niels was an outstanding student, though not in the conventional sense. He was quiet, reflective, and deeply focused, often lost in thought when others were content with memorization. His teachers quickly noticed his remarkable gift for understanding abstract problems. Mathematics and physics became his favorite subjects, though he also excelled in philosophy and language. He approached learning as a journey of discovery, not a race for grades. His classmates often described him as the boy who thought too deeply, but to Niels, thinking was as natural as breathing. His secondary education took place at Gammelholm Grammar School, one of Copenhagen's finest institutions. There, he found teachers who encouraged his curiosity rather than restricting it. One of his mentors, a mathematics instructor, once remarked that Niels had a mind that sees connections where others see divisions. That ability to link ideas across disciplines would become the signature of Bohr's genius. During this time, he began reading the works of great scientists like Newton, Maxwell, and Thomson. The laws of nature fascinated him, but he also sensed that something was missing, a hidden layer of reality not yet revealed by classical physics. The late 19th century was a time of transformation in science. The discoveries of electromagnetism, thermodynamics, and atomic theory had reshaped humanity's understanding of matter and energy. Yet, questions remained unanswered. What was the true nature of the atom? How did energy move between particles? Why did light behave both as a wave and a particle? These mysteries stirred something within Niels Bohr even before he entered university. He could feel that the universe still held secrets beyond the reach of Newton's equations, waiting for a new kind of thinker to unveil them. When Niels entered the University of Copenhagen in 1903, he stepped into an intellectual world that was both exciting and uncertain. Physics was on the brink of revolution, and Bohr was among the young minds ready to challenge its foundations. He began his studies in physics under the guidance of Christian Christensen, a respected physicist and the only professor of theoretical physics at the university at the time. Christensen was known for his rigorous approach, but also for his openness to new ideas, a combination that would shape Bohr's own philosophy of science. Bohr immersed himself completely in his studies. His notebooks from this period reveal an extraordinary depth of thought and a meticulous attention to detail. He conducted experiments with liquids and surface tension, a topic that fascinated him because it seemed to bridge the gap between the visible and invisible forces of nature. His first major research paper, written as a student, explored how vibrations affected the surface tension of water jets. The paper was so precise and original that it earned him a gold medal from the Royal Danish Academy of Sciences and Letters. More importantly, it revealed a defining trait of Bohr's mind, the ability to combine theory with experiment, imagination with logic. Despite his growing achievements, Bohr remained humble. He often doubted his own work, not because he lacked confidence, but because he sought perfection in understanding. He would re-examine every assumption, every formula, asking himself whether it truly described the reality behind the numbers. This restless curiosity was not mere academic discipline. It was the heartbeat of his character. For Bohr, science was not about being right, but about getting closer to truth. Outside the classroom, Bohr was known for his modest and kind personality. He was tall, quiet, and thoughtful, with an intensity that drew people toward him. Friends and professors admired his sincerity and patience. He never dismissed anyone's ideas, no matter how simple or mistaken they seemed. Instead, he would listen carefully, pause, and then respond with insight that revealed layers of meaning others had overlooked. This unique manner of communication, calm, deliberate, and profound, became one of his most distinctive traits throughout his life. His years at university were also years of deep reflection. Bohr read widely, not just in science but in philosophy and literature. He was fascinated by the writings of Kierkegaard, another great Dane whose ideas about paradox, faith, and uncertainty would later echo in Bohr's own interpretation of quantum mechanics. The philosophical foundations of Bohr's thought were being laid long before he encountered the quantum world. He believed that knowledge was not absolute but contextual, a belief that would later form the essence of his principle of complementarity. In 1909, Bohr completed his master's degree and began work on his doctoral thesis, which focused on the electron theory of metals. At that time, physicists struggled to explain how electrical conductivity and magnetism operated inside metals. Bohr approached the problem with characteristic thoroughness, examining every aspect of existing theories and pointing out their limitations. His dissertation, though dense and technical, demonstrated a level of insight that set him apart from his peers. It revealed his ability to see beyond equations, to sense the underlying principles guiding nature's behavior. When Bohr defended his doctoral thesis in 1911, he impressed his examiners with his command of both mathematics and physical intuition. But he was not satisfied. He felt that even the most sophisticated classical models failed to explain the true structure of matter. Around this time, he began studying the emerging ideas of atomic physics, especially those related to J.J. Thomson's discovery of the electron and Ernest Rutherford's nuclear model. These concepts sparked his imagination, but Bohr sensed that something deeper was missing. He knew that a new framework was needed, one that could unify the puzzling results of experiments with the elegant logic of theory. The same year, Bohr traveled to England, where he joined J.J. Thomson's laboratory at Cambridge University. This journey marked a turning point in his intellectual life. The bustling world of British science exposed him to cutting-edge research, but also to the limitations of the existing models. Bohr admired Thomson's brilliance, yet he found the atomic theories of the time unsatisfactory. They failed to explain why atoms were stable or how electrons behaved inside them. Bohr's restless mind began forming new ideas that would eventually lead to his quantum model of the atom. In Cambridge, Bohr struggled at first to fit in. English was not his first language, and his quiet Danish manner was easily mistaken for shyness. But behind that reserved exterior was a mind alive with possibilities. He would spend hours in the lab, conducting experiments, jotting down notes, and sketching diagrams. He was driven not by ambition, but by an almost spiritual desire to understand the truth behind nature's mysteries. His correspondence from that time reveals his inner conflict, a blend of awe, doubt, and determination. He wrote to his family about how different the scientific atmosphere was in England, yet how it inspired him to think more freely. After a short period at Cambridge, Bohr moved to the University of Manchester to work under Ernest Rutherford, who had recently proposed the nuclear model of the atom. Rutherford's discovery that atoms consist of a dense central nucleus surrounded by electrons was revolutionary, but it raised a troubling question. If electrons orbit the nucleus like planets around the sun, why don't they lose energy and spiral inward? Bohr found himself captivated by this puzzle. Though it lay beyond the education phase of his life, the seeds of his greatest discovery were already sprouting. By this stage, Bohr's education had become something larger than formal study. It was a lifelong process of questioning and reimagining the laws of nature. From his father's laboratory conversations to his experiments in Copenhagen, from philosophical musings to scientific rigor, every experience had shaped the young man who would one day redefine physics. His upbringing had given him empathy, his schooling had given him structure, and his mind had given him the courage to explore the unknown. As the first decade of the 20th century drew to a close, Niels Bohr stood on the edge of a new world. He had mastered the knowledge of his time, but more importantly, he had learned how to challenge it. He had come to understand that science was not about final answers, but about evolving questions. The journey that began in the warm, book-filled home of his childhood had now reached the threshold of discovery. The boy who once gazed curiously at the ripples of water would soon gaze into the ripples of energy that govern the universe itself. The story of his early life and education is not just a record of academic milestones. It is the story of how a gentle, inquisitive mind grew into one of the greatest scientific thinkers of all time. Niels Bohr's path was built not on certainty, but on wonder. And it was that wonder, born in the quiet streets of Copenhagen, that would lead him to unlock the quantum secrets of the atom and reshape our understanding of reality forever. In the laboratories of Manchester, the hum of conversation and the faint crackle of electrical instruments filled the air. Niels Bohr, now in his mid-20s, moved quietly among the benches, his notebook always close at hand. Though still considered a student, he carried himself with the seriousness of a thinker searching for the foundations of truth. His education had reached a new dimension, no longer confined to textbooks and lectures. It was now shaped by collaboration, experimentation, and the living pulse of discovery. Working under Ernest Rutherford was both exhilarating and intimidating. Rutherford was already a towering figure in physics, known for his bold experiments and his booming laugh that could echo across the corridor. He was a man of intuition and courage, and Bohr admired that deeply. Yet their styles were different. Rutherford's approach was direct and experimental, while Bohr's was reflective and theoretical. Where Rutherford saw results, Bohr saw patterns. Where Rutherford confirmed data, Bohr searched for meaning. This contrast between the experimental and the philosophical would become the crucible in which Bohr's ideas were forged. During his time in Manchester, Bohr continued studying the behavior of electrons and the structure of atoms. The scientific community at that moment was teetering on the edge of something monumental. The discovery of radioactivity, the new insights into the electron, and the unresolved mystery of atomic stability filled every conversation. For Bohr, these weren't just problems to be solved, they were clues to a deeper truth. He believed that the visible behavior of matter hinted at invisible rules, rules that classical physics could not fully describe. It was here that Bohr's education became inseparable from his creativity. Late into the night, he would sit in his small room, reviewing his notes, scribbling equations, and imagining new possibilities. Sometimes he would rise suddenly, pacing the floor, muttering softly in Danish as ideas collided and merged in his mind. His colleagues remembered him as both gentle and intense, a man whose eyes revealed a quiet fire, the kind that burns only in those who sense the future before others do. Though Bohr's formal education was nearing completion, he never stopped learning. Every conversation, every failed experiment, every philosophical question became a teacher. He once remarked that every valuable human being must be a radical and a rebel. And in science, he was precisely that, respectful of tradition but unafraid to challenge it. In Manchester, he began to question the assumptions of classical mechanics that had dominated physics for centuries. He knew that Newton's laws worked beautifully for planets and projectiles, but they faltered when applied to the tiny world of electrons and atoms. Somewhere between these scales, a hidden order was waiting to be discovered. Bohr's curiosity about the atom was not simply academic, it was personal. He often thought back to his father's teachings about life and physiology. Just as his father had tried to understand the mysteries of the living body, Bohr was now seeking to understand the living structure of matter itself. The continuity between biology and physics fascinated him, the idea that both realms might obey subtle, interconnected principles. He carried with him the same reverence for nature that had filled the Bohr home in Copenhagen, where knowledge and humility went hand in hand. When he returned briefly to Denmark in 1912, Bohr was no longer merely a student, he was a scholar poised for transformation. The University of Copenhagen welcomed him back as one of its brightest young physicists. His professors recognized that his understanding of theory had deepened into something rare, an ability to see physical reality not as a set of isolated facts, but as an evolving whole. It was around this time that Bohr married Margrethe Endyrar Lund, a woman whose calm strength and insight would sustain him through the challenges ahead. Their relationship was one of quiet partnership. She became not only his wife but his confidante, translator, and intellectual companion. She would later play a vital role in articulating Bohr's complex ideas to the world. Back in his homeland, Bohr's education took on a new form, teaching. As he lectured and mentored students, he discovered that explaining ideas to others refined his own understanding. He would pace the lecture hall slowly, speaking in his measured voice, pausing often as though weighing every word. To some, his manner seemed hesitant. To those who knew him, it was the rhythm of deep thought. He refused to oversimplify complex ideas because he believed that truth deserved patience. His students learned not only physics from him, but a way of thinking precise, humble, and endlessly curious. Around 1912, Bohr received a fellowship that allowed him to continue his research abroad, and he decided to return to Rutherford's laboratory in Manchester. This time, he was armed with new questions and a sharper vision. He began re-examining the structure of the atom in light of the discoveries of Max Planck and Albert Einstein. Planck's concept of energy quanta, the idea that energy comes in discrete packets, had unsettled the world of classical physics. Einstein had extended this idea to explain the photoelectric effect, showing that light itself behaved as if made of particles. To Bohr, these discoveries hinted that nature was far stranger and more elegant than anyone had imagined. He started to combine these revolutionary ideas with Rutherford's nuclear model. If electrons moved around a dense nucleus, perhaps they did not move continuously, as classical physics assumed, but in specific, quantized orbits. Perhaps they could jump between these orbits by absorbing or emitting energy in fixed amounts. The thought electrified him. He was beginning to see how the invisible architecture of the atom could be governed by quantum rules. How stability, light emission, and the spectral lines of hydrogen could all be explained within a single framework. The education that began in his childhood curiosity had now ripened into world-changing insight. But before Bohr could finalize his theory, he needed to understand every piece of the puzzle. He spent months re-analyzing experimental data and mathematical equations. Every calculation felt like a step into the unknown. He had long since moved beyond the safety of established theories. His early education had taught him that progress required the courage to stand alone in doubt. At times, his ideas seemed too bold even to himself. He would write, erase, rewrite, and question again. Yet the more he questioned, the clearer his conviction became. Nature operated in ways that classical reasoning could not fully capture. The years of disciplined learning had prepared him for this moment. His training in precision from his father, his mastery of mathematics from his school days, his exposure to philosophical thought, and his deep respect for experiment, all converged to shape the unique mind that would soon propose the quantum atom. The boy who once built makeshift experiments in his family home now stood on the brink of transforming physics. By the time he published his famous trilogy of papers on atomic structure in 1913, Bohr's education had effectively completed its metamorphosis into discovery. Yet even as he revealed his revolutionary model, the idea that electrons occupy quantized energy levels around the nucleus, he remained the same modest thinker who saw himself as a perpetual student. For Bohr, learning never ended. Understanding was a horizon that moved farther away the closer one approached it. Looking back, one can see that Bohr's early life was a perfect balance of intellect and imagination, of discipline and freedom. His childhood home taught him to ask questions without fear. His schools taught him to pursue those questions with rigor. His mentors taught him to test ideas against reality. Together, these experiences created the foundation of a mind capable of bridging the old and new worlds of physics. Even after his atomic model gained international recognition, Bohr continued to draw upon the lessons of his formative years. His humility came from his family, his patience from his teachers, his daring from the spirit of scientific inquiry that had surrounded him since birth. When he later established the Institute for Theoretical Physics in Copenhagen, known today as the Niels Bohr Institute, he modeled it on the atmosphere of his childhood home, open, collaborative, and filled with dialogue. He wanted young scientists to experience the same nurturing of curiosity that had defined his own education. In the broader sweep of history, Bohr's early years reveal something timeless about the nature of learning itself. True education, as his life shows, is not about memorizing facts or collecting honors. It is about cultivating a state of mind, one that blends wonder with skepticism, knowledge with humility. Bohr never sought to conquer nature, he sought to understand it. And that attitude, more than any formula or theory, became his greatest contribution to science. When we imagine the young Niels Bohr walking through the streets of Copenhagen, hands in his pockets, mind adrift in thought, we glimpse a truth about genius. It rarely appears as lightning, it grows slowly, nurtured by environment, discipline, and love. Bohr's brilliance was not the product of isolation, but of connection to his family, his teachers, his peers, and to the ever-mysterious world that beckoned him to explore. In the quiet moments of reflection late in his life, Bohr often spoke about the importance of paradox in human understanding. He would say that the opposite of a profound truth may well be another profound truth. This way of thinking can be traced directly back to his formative years, to the philosophical debates he absorbed as a student, to the tolerant and questioning spirit of his home, to his realization that knowledge grows through contradiction. His early education had not merely filled his mind, it had shaped his worldview, teaching him that progress comes not from certainty, but from the courage to live with uncertainty. The lessons of his youth echoed throughout his career. When faced with the enigmas of quantum mechanics, Bohr drew upon his early habit of seeing complexity where others saw simplicity. When other scientists argued for absolute answers, he argued for complementarity, the idea that different perspectives could each reveal part of the truth. This philosophy, though born in the quantum world, had its roots in the intellectual soil of his childhood. As the camera of imagination pulls back, we can see the arc of his early life like a carefully drawn curve. From the warm glow of family learning to the bright laboratories of Europe, from the curious child to the scholar who dared to rethink the universe. Every chapter of his education was a step toward that defining moment when he would unveil a model of the atom that forever changed human knowledge. Yet even then, he remained the student, the listener, the questioner. The story of Niels Bohr's early life and education is, in essence, the story of how curiosity becomes creation. It reminds us that the roots of discovery lie not in brilliance alone, but in the gentle shaping of a mind that never stops asking why. From the whispering halls of his childhood home to the echoing laboratories of Cambridge and Manchester, Bohr's journey was one long conversation with nature. A conversation that began with a question and grew into a legacy that continues to inspire every scientist who dares to dream beyond the visible. And so, before Niels Bohr became the father of quantum theory, he was first the child of curiosity. Raised in a world where wonder was wisdom, and education was not an end but a lifelong adventure. It was this unbroken chain of learning, stretching from his earliest observations to his most profound discoveries, that made him not only a scientist of unparalleled vision, but also a symbol of what it means to learn, to question, and to seek truth in a universe filled with mystery. In the early years of the 20th century, science was standing at the edge of an abyss of mystery. The old world of classical physics, built on the certainties of Newton and Maxwell, was beginning to tremble under the weight of new discoveries. The atom, once thought to be indivisible and eternal, had been shattered into parts, electrons, protons, and an unexplored void that defied logic. The universe, it seemed, was no longer the simple clockwork of the Enlightenment. It had become a puzzle of invisible forces and strange behaviors. Amid this intellectual storm, a quiet Danish physicist named Niels Bohr was preparing to do what few had dared: to look into the atom's heart and describe the order within its apparent chaos. Bohr arrived in Manchester in 1912 with questions burning in his mind. The young scientist carried with him not the arrogance of youth, but the calm intensity of a thinker who sensed that something profound was waiting to be discovered. In Ernest Rutherford's laboratory, he found both inspiration and contradiction. Rutherford had recently overturned the old, plum-pudding, model of the atom, which imagined electrons scattered like raisins within a diffuse positive charge. His famous gold foil experiment had revealed a startling truth. Most of the atom was empty space, with a tiny, dense nucleus at its center. It was a discovery that redefined matter itself, yet it left physicists puzzled. If electrons were truly orbiting the nucleus, why didn't they lose energy and crash inward, as the laws of electromagnetism predicted? According to classical physics, such atoms could not exist for more than a fraction of a second. And yet the world was clearly stable. Bohr could not ignore this contradiction. To him, the universe was rational, but only if one learned to listen to it in a new language. He began to wonder whether the problem lay not in the atom, but in the assumptions of physics itself. What if the laws that govern planets and pendulums did not apply in the same way to the tiny world of electrons? What if there was another order, a deeper principle, hidden beneath the surface of classical theory? In his modest workspace in Manchester, Bohr started constructing that new order. He examined the latest experimental results with a philosopher's patience. The spectra of hydrogen, those thin, colored lines emitted when gas was excited, seemed to hold a secret code. Each line represented a specific frequency of light, and every frequency meant a specific amount of energy. For decades, scientists had observed these lines, mapping them with mathematical precision, but no one understood why they appeared in such a pattern. To Bohr, these spectral fingerprints were not random. They were messages from the atom, revealing its internal structure in numbers and light. Bohr's mind began to assemble the pieces. He took Rutherford's nuclear model and combined it with Max Planck's revolutionary concept of quantization. The idea that energy is not continuous, but comes in discrete packets called quanta. It was a daring synthesis. Classical theory said that electrons could orbit the nucleus at any distance, but Bohr proposed something radically different. Electrons could only exist in certain allowed orbits, each corresponding to a fixed energy level. Between these levels, there was no in-between, no halfway state. When an electron jumped from one orbit to another, it absorbed or emitted a quantum of light, a photon, whose energy matched the difference between those levels. It was an audacious idea, one that defied the intuition of even the greatest physicists of the time. To many, it sounded absurd. How could something as smooth and continuous as motion suddenly jump from one state to another without passing through the space in between? Yet Bohr trusted the mathematics, and more than that, he trusted nature's own signals. The hydrogen spectrum matched his theory perfectly. Every color line, every wavelength corresponded exactly to the transitions his equations predicted. The atom, for the first time, began to make sense. The year was 1913. Bohr published 3 papers under the title, On the Constitution of Atoms and Molecules. The language was cautious, but the implications were explosive. In those pages, he laid out the framework that would become the foundation of quantum theory. He described how electrons revolved around a small, positively charged nucleus in specific, quantized orbits. He explained how light was emitted when an electron leapt from a higher to a lower orbit. And he showed that the atom, far from being a chaotic whirl of particles, was governed by elegant mathematical laws that balanced stability and motion in a dance of energy. Bohr's atomic model was a bridge, one foot in the classical world, one in the emerging quantum realm. It preserved the mechanical imagery of orbits and forces while introducing the radical idea that energy itself was quantized. It was this balance that made the theory both revolutionary and understandable. For the first time, scientists could visualize the invisible. The atom was no longer an abstract mystery, it had structure, symmetry, and logic. When his papers appeared, the response was immediate and intense. Across Europe, physicists debated the implications of Bohr's ideas. Some dismissed them as speculation, others hailed them as genius. Even Rutherford, Bohr's mentor, admitted that the young Dane had jumped the classical fence into unknown territory. Albert Einstein, always intrigued by bold ideas, wrote to congratulate Bohr, though he remained skeptical of the theory's deeper meaning. But the evidence was undeniable. Bohr's model explained the spectral patterns of hydrogen with a precision unmatched by any previous theory. It was a triumph of simplicity and imagination, a clear window into the atom's hidden order. As his fame spread, Bohr remained remarkably modest. He did not see himself as a revolutionary, but as a student of nature's mysteries. In his letters, he often described his excitement at finding coherence in the chaos, but also his doubts. He knew that his model, while powerful, was incomplete. It described hydrogen perfectly but struggled to account for more complex atoms. It was a step forward, but only a step, yet in science, such steps open entire new worlds. In the summer of 1913, Bohr returned to Copenhagen as a rising star. He was greeted not as a triumphant hero, but as a thoughtful scholar who had quietly rewritten the laws of the microscopic universe. The University of Copenhagen offered him a professorship, and he began to build the foundation of what would become a new center for theoretical physics. Students flocked to his lectures, drawn by his calm manner and the quiet authority of a man who had touched the frontier of knowledge. When Bohr spoke about the atom, his words carried a kind of poetry. He described electrons not as mere particles, but as participants in a cosmic rhythm, moving in harmony with laws that transcended classical logic. He often paused mid-sentence, searching for words to match the depth of his thought, aware that language itself was struggling to keep pace with the discoveries of physics. His students later said that Bohr taught them not just how to think scientifically, but how to wonder scientifically. What made Bohr's model so groundbreaking was not only its accuracy but its philosophy. It challenged the very nature of reality. In his vision, the atom was not a miniature solar system obeying predictable paths. It was a quantum structure where certainty gave way to probability, where energy came in jumps, and where observation itself played a role in defining what could be known. Though these ideas would be expanded later by Heisenberg, Schrödinger, and others, the seed was already there in Bohr's 1913 papers, the recognition that the microscopic world followed rules entirely different from those of everyday experience. Bohr's work also marked a profound shift in the relationship between theory and experiment. Until then, physics had been largely descriptive, explaining observed phenomena through known laws. Bohr's model, by contrast, was predictive. It told scientists what to expect, revealing hidden connections between mathematics and measurement. When later experiments confirmed his predictions, it was a moment of vindication not just for Bohr, but for the new age of theoretical physics he represented. The impact of Bohr's atomic model rippled far beyond the laboratory. It inspired a generation of scientists to explore the strange new landscape of quantum behavior. It also challenged philosophers to reconsider the meaning of knowledge and observation. If the atom's structure could change depending on how it was measured, what did that say about the limits of human perception? Bohr himself approached these questions with humility. He did not see his model as a final truth, but as a provisional step toward a deeper understanding. Every great and deep difficulty, he once said, bears in itself its own solution. It forces us to change our thinking in order to find it. In the years that followed, Bohr's model was refined and expanded. Sommerfeld introduced elliptical orbits to account for finer details of atomic spectra, and new quantum ideas emerged that would eventually replace the image of definite orbits with wave functions and probabilities. Yet even as quantum mechanics evolved, Bohr's vision remained its cornerstone. His model had given scientists a language to speak about the invisible, a way to think about the atom as a structured, quantized entity rather than a chaotic cloud. By 1914, Bohr had become an international figure in physics, though he continued to live a simple, disciplined life. He spent long hours in his study, walking back and forth, whispering equations under his breath, and pausing only to sip tea or jot down a sudden idea. His colleagues sometimes found his pace of thought overwhelming, not because he moved quickly, but because he moved deeply. When he discussed an idea, he explored it from every angle, probing its meaning until it either collapsed or revealed its truth. That intensity, shaped by years of reflection and learning, gave him a kind of scientific intuition that few could match. Bohr's atomic model was more than a scientific breakthrough. It was a turning point in human understanding. It shattered the last illusion of the mechanical universe and opened the door to a reality ruled by probability and paradox. In doing so, it laid the foundation for technologies that would define the modern world: lasers, semiconductors, nuclear energy, and quantum computing. Yet Bohr himself remained uninterested in fame or practical application. For him, the joy was in the discovery, in the quiet moment when an equation revealed a glimpse of the universe's hidden order. As Europe slid toward the chaos of World War I, Bohr continued his work, isolated yet absorbed in thought. The conflict raged outside, but within his mind the world was one of light, energy, and symmetry. In a letter to a colleague, he wrote, "It is strange that we can find in the smallest things a reflection of the greatest." To him, the atom was not just a physical object, but a metaphor for harmony. A reminder that even amid turbulence, nature maintained its balance through invisible laws. By the time the war ended, The scientific world had changed forever, and Bohr's model stood at the center of that transformation. His education, his patience, his philosophical depth, all had converged in those years to produce an idea that would endure for generations. The model of the atom was not just a diagram, it was a symbol of a new kind of science. One that embraced mystery, acknowledged limits, and sought meaning beyond the visible. Bohr's journey to that moment had been long and filled with doubt, but it was his willingness to think differently, to accept the paradoxical, that allowed him to see what others could not. In the delicate balance of theory and imagination, he found truth. And in that truth, he gave humanity a new way to understand itself, as part of a universe far stranger and more beautiful than anyone had ever imagined. As the months passed after Bohr released the first outline of his atomic theory, a quiet revolution began rippling through the scientific world. Many could not immediately grasp what he was proposing, that the atom, long thought to be a miniature solar system of electrons freely orbiting the nucleus, followed a hidden logic based on precise, discrete packets of energy. It was a daring suggestion that contradicted classical mechanics, yet Bohr's calm reasoning and experimental evidence gave it an air of inevitability. Across Europe, laboratories buzzed with discussions about these mysterious quantum jumps. Some physicists dismissed the idea as too abstract, while others sensed that Bohr had uncovered something profound about nature itself. In Copenhagen, Bohr's small office became a hub of activity. Students and visiting scientists crowded around blackboards, covered with chalk marks, as Bohr gently guided them through his equations. He was known for pacing slowly, hands folded behind his back, listening carefully before speaking. He preferred dialogue to declaration, often asking questions that made his listeners examine what they thought they understood. His calm Danish accent carried both warmth and precision, and even the most skeptical visitors left with a feeling that they had glimpsed a new way of seeing the universe. The hydrogen atom, simple as it seemed, became the stage on which Bohr demonstrated the power of his model. Its spectral lines, those delicate bands of light emitted when hydrogen gas was energized, had puzzled scientists for decades. Bohr showed that each line corresponded to an electron shifting between specific energy levels. When an electron dropped from a higher orbit to a lower one, it released a photon with an energy equal to the difference between those two levels. The wavelengths of these photons matched the observed spectral lines exactly. For the first time, the mathematics and the measurements sang in harmony. This elegant agreement between theory and experiment transformed Bohr from a promising young theorist into a leader of a scientific revolution. Newspapers in Denmark began calling him a national treasure, while journals across Europe published detailed analyses of his model. Yet Bohr himself remained humble. He often reminded his colleagues that any model of the atom was only a picture, a way of thinking, not a literal description of what existed inside matter. The true atom, he insisted, was far more mysterious than human language could capture. Still, his model had opened a door through which an entirely new physics would soon step. The years following 1913 were a time of intense excitement and debate. In Manchester, Rutherford praised his former students' courage, but remained puzzled by the strange quantization rules. In Germany, Planck and Einstein both recognized the model's power, though Einstein privately expressed doubts about the abrupt quantum jumps, which seemed to defy continuous laws of motion. Young physicists such as Sommerfeld, Born, and Pauli took Bohr's ideas and expanded them, developing more sophisticated mathematical tools that extended his model to heavier atoms. Each new refinement brought more evidence that the quantum world operated by its own set of principles, distinct from classical intuition. Bohr watched these developments with cautious pride. He saw the quantum as a necessary correction to the arrogance of classical physics, which had assumed that the universe could be entirely explained by deterministic laws. To him, the quantum symbolized both limitation and possibility, a reminder that nature set boundaries on what could be known, even as it invited deeper inquiry. He believed that this humility before nature's mystery was the essence of true science. World War I briefly interrupted the flow of research. Europe was consumed by conflict, and scientific communication across borders became nearly impossible. Bohr, who remained in neutral Denmark, continued to refine his theories in isolation. He spent long evenings at his desk, examining the mathematical foundations of his model, searching for deeper patterns beneath the equations. He also began writing letters to colleagues who were now soldiers or refugees, offering words of encouragement and hope for a future when science could once again unite rather than divide. When peace finally returned, the world Bohr re-entered was both scarred and hungry for renewal. The 1920s would prove to be a golden decade for physics, and Bohr stood at its center. His atomic model, once a radical proposal, now served as the starting point for an entire generation of young theorists determined to understand the quantum world in full detail. Among them was a gifted German physicist named Werner Heisenberg, who arrived in Copenhagen eager to learn from the master. Bohr recognized Heisenberg's brilliance immediately, and together they began exploring the strange logic that governed the subatomic realm. Their collaboration would soon lead to quantum mechanics itself, the grand successor to Bohr's early atomic theory. But before that new theory could take shape, Bohr's own model had to face its limitations. The simple circular orbits he had proposed worked beautifully for hydrogen, but failed for more complex atoms. Electrons in multi-electron systems refused to fit neatly into the tidy energy levels his formulas predicted. Spectral lines split and blurred in ways his equations could not explain. Instead of being discouraged, Bohr saw these failures as signposts pointing the way forward. Nature, he often said, reveals herself not in perfection but in contradiction. Each inconsistency was a clue, each anomaly a door waiting to be opened. He encouraged his students to embrace these puzzles, to think not of electrons as tiny planets, but as entities whose behavior defied everyday logic. Slowly, the idea began to emerge that electrons might not move in well-defined orbits at all, but rather exist in regions of probability, a concept that would later become central to quantum mechanics. Though this shift would eventually render Bohr's original model obsolete, he accepted the change with grace. He understood that science was a living process, and that even the most successful theory must eventually give way to a deeper truth. Copenhagen in the mid-1920s became the beating heart of the quantum revolution. The Institute for Theoretical Physics, founded by Bohr in 1921, became a haven for the brightest minds in Europe. There was an atmosphere of quiet intensity in its narrow hallways, where chalk dust floated like fine snow in the sunlight. Conversations about the nature of reality carried on late into the night. Young scientists from Germany, England, and even America made the pilgrimage to meet Bohr, to argue with him, to be shaped by his calm but relentless curiosity. Visitors often remarked on the rhythm of life at the Institute. Mornings began with quiet study, followed by long lunches filled with laughter, then deep philosophical discussions that lasted until dusk. Bohr's presence infused the building with a sense of purpose. He rarely gave direct orders or instructions. Instead, he guided by questioning, by offering gentle paradoxes that forced his students to think in new ways. He seemed to believe that truth could not be handed down, but had to be discovered through struggle and dialogue. The impact of Bohr's atomic model reached far beyond the scientific community. It captured the imagination of artists, writers, and philosophers who saw in it a reflection of a broader cultural shift, a move away from rigid certainty toward ambiguity and complexity. The atom, once imagined as a solid, predictable structure, was now revealed to be a world of motion, chance, and mystery. This mirrored the mood of a post-war Europe grappling with uncertainty about its own future. Bohr's theory, though deeply technical, spoke to something universal, the realization that even the smallest things in nature could harbor infinite complexity. In lectures across the continent, Bohr emphasized that the atomic model was not merely a tool for calculation, but a philosophical milestone. It forced humanity to confront the limits of knowledge, He explained that the classical view of measurement, the idea that we can observe something without altering it, could no longer hold true. At the quantum level, the act of observation itself changed what was being observed. This notion, unsettling to many, became the cornerstone of his later complementarity principle, but its roots were already present in his atomic theory. By the mid-1920s, Bohr's model had achieved something extraordinary. It had predicted, inspired, and then transcended itself. It became both the foundation and the stepping stone of modern physics. The equations that once seemed so revolutionary now served as the gateway to an even stranger world, where probability replaced certainty and waves merged with particles. Yet even as others refined and replaced his ideas, Bohr remained their quiet guardian, reminding everyone that understanding grows through contradiction, and that humility is the scientist's greatest virtue. His colleagues often spoke of Bohr's unusual patience. He would listen to an argument for hours, pause thoughtfully, and then respond with a question so profound that it reframed the entire discussion. His mind worked like a mirror, reflecting each idea back in a new light. This quality made him not just a great theorist, but a remarkable teacher. Many who studied under him went on to win Nobel Prizes themselves, carrying forward the spirit of inquiry that Bohr had instilled. In 1922, less than a decade after publishing his atomic model, Bohr received the Nobel Prize in Physics. The citation praised him for his investigations of the structure of atoms and the radiation they emit. When the announcement reached Copenhagen, the entire city erupted in celebration. Newspapers ran stories describing him as the man who had unlocked the atom's secret. Yet Bohr himself seemed almost embarrassed by the attention. During his acceptance speech in Stockholm, he spoke not of triumph but of gratitude. To Rutherford, to Planck, to his family, and to the countless others whose insights had paved the way. He described science as a collective human endeavor, where each discovery builds on the foundation laid by others. The Nobel Prize marked not the end of Bohr's work, but a new beginning. With recognition came responsibility. He used his fame to secure funding for his institute and to promote international collaboration in science. He envisioned a future in which research transcended national boundaries, where physicists could share knowledge freely for the advancement of humanity. His atomic model had shown that even the most fundamental truths were interconnected. He believed human societies should reflect that same unity. As the decade drew to a close, the scientific world was preparing for another leap. The seeds Bohr had planted were blossoming into quantum mechanics, a theory that would soon transform not just physics, but the entire worldview of modern civilization. Yet at its core, this revolution still bore the unmistakable imprint of Bohr's atomic model. It had introduced the radical idea that energy came in quanta, that electrons occupied distinct levels, and that observation played a central role in shaping physical reality. Those principles remained the heartbeat of quantum theory. No matter how sophisticated the mathematics became, looking back, one can see that Bohr's atomic model was both a scientific achievement and a philosophical awakening. It reminded humanity that knowledge does not advance in a straight line, but through leaps of imagination. It taught that mystery is not a flaw in our understanding, but a sign of the universe's depth, and it showed that even the smallest particle of matter can challenge the boundaries of reason and reveal the poetry hidden within physics. By the time Bohr's early model gave way to the full machinery of quantum mechanics, its influence had already become permanent. The world's understanding of matter, energy, and light would never be the same again. In laboratories, in classrooms, and in the pages of textbooks, the ghost of Bohr's atom continued to glow, a symbol of the moment when humanity first peered into the quantum realm and found both order and wonder waiting inside. In the early decades of the 20th century, the air of science was charged with mystery. A strange tension had begun to build between the world described by classical physics and the new reality emerging from experiment after experiment. The comfortable laws of Newton, that had guided human understanding for centuries were starting to falter when confronted with the smallest building blocks of matter. Energy, once thought to flow in continuous streams, was behaving as if it arrived in tiny, discrete packets. Light, long understood as a wave, sometimes acted like a particle. And in the midst of this growing confusion stood a young Danish physicist, Niels Bohr, trying to make sense of it all. Bohr had already shaken the scientific world with his atomic model, but he sensed that his discovery was only the beginning. Beneath the structure of the atom lay something even more elusive, a hidden order that defied the logic of everyday experience. He felt that if one could truly grasp the nature of energy exchange inside the atom, it would unlock the secret code of the universe itself. That quest led him into the realm of quantum theory, a world where certainty gave way to probability, and where reality itself seemed to bend under observation. The roots of quantum theory traced back to a German physicist, Max Planck, who in 1900 introduced a daring idea to solve an obscure problem. He had been studying blackbody radiation, the way objects emit light when heated, and found that classical physics failed to describe the observed pattern. To make his equations work, Planck proposed that energy could not be emitted continuously, but only in discrete chunks, which he called quanta. It was a mathematical trick, or so he thought. Yet, as time passed, the implications of his assumption began to echo far beyond his original intention. Bohr was captivated by this idea. Planck's quantum offered a way to explain the behavior of electrons in his atomic model, but Bohr believed it meant something deeper than just a convenient formula. It hinted that nature itself was quantized, that the universe operated through a series of jumps and limits, not smooth transitions. This realization unsettled many scientists of his time. The classical world had been built on the notion of continuity, where causes flowed naturally into effects. The quantum world, by contrast, appeared fragmented and unpredictable. To Bohr, this wasn't a failure of understanding, but a sign that the universe was far more subtle than human intuition allowed. He began to study the mathematical patterns of energy transitions within atoms, searching for order within the apparent chaos. His atomic model already described electrons moving between fixed orbits, but the mechanism behind these transitions remained mysterious. How did an electron decide when to jump? Where did the emitted photon come from? And why did it always have exactly the right amount of energy? Bohr wrestled with these questions late into the night, often pacing his study in silence, his mind moving between equations and imagination. As he delved deeper, Bohr started to see a connection between the act of observation and the behavior of atomic systems. He realized that at the microscopic scale, measurement was not a passive act. When one observed a system, when one tried to detect an electron or measure its position, the very act of doing so disturbed it. This was not merely a technical inconvenience, but a fundamental truth about nature. In the quantum realm, the observer and the observed could not be separated. It was a shocking idea, one that would come to define the philosophical heart of quantum theory. The first clear experimental evidence supporting these strange ideas came from the work of Albert Einstein, who in 1905 explained the photoelectric effect. He showed that light could behave like a stream of particles, or photons, each carrying a quantum of energy. Bohr studied Einstein's work carefully, and though he admired its brilliance, he also recognized its paradoxical nature. If light could act like a particle, and matter could behave like a wave, what did that say about the true nature of reality? The neat boundaries between energy and matter, wave and particle, seemed to dissolve. In the years following his atomic breakthrough, Bohr corresponded extensively with Einstein, Planck, and other pioneers who were struggling to make sense of this new picture of the universe. Their letters read like philosophical dialogues as much as scientific discussions, exchanges filled with curiosity, doubt, and wonder. Bohr often argued that the apparent contradictions of quantum behavior were not flaws but reflections of a deeper harmony. To him, nature was not chaotic but complementary. Opposing descriptions, such as wave and particle, could both be true, depending on how one looked. But the equations alone were not enough to describe this duality. What was needed was a new language of physics, a framework that could unite energy, matter, and observation into a coherent picture. By the early 1920s, young theorists across Europe were working to build such a framework. Werner Heisenberg developed his matrix mechanics, which described atomic systems through abstract mathematical relationships rather than physical trajectories. Erwin Schrödinger introduced his wave equation, portraying electrons not as point-like particles, but as smeared-out waves of probability. Paul Dirac and others added their insights, connecting quantum ideas with relativity and symmetry. Bohr watched these developments with fascination. Though he had laid the conceptual foundation, he was humble enough to recognize that the younger generation was giving the quantum world its mathematical voice. Heisenberg, in particular, had been deeply influenced by Bohr's way of thinking. When Heisenberg presented his new theory during a visit to Copenhagen in 1925, Bohr listened intently. The two men debated for hours, walking through the gardens near Bohr's institute, scribbling equations on scraps of paper. By morning, both were exhausted but exhilarated. They knew they were standing on the threshold of something historic. Bohr's role in the formation of quantum mechanics went far beyond equations. He became the interpreter, the philosopher of the quantum world. He recognized that the new theory did not just describe physical phenomena, it challenged the very nature of knowledge itself. How could one speak of an atom's position or momentum when the act of measuring one changed the other? How could something exist as both a particle and a wave until it was observed? These questions reached beyond physics, touching the deepest philosophical and even spiritual concerns of humanity. As he pondered these mysteries, Bohr formulated one of his most enduring ideas, the principle of complementarity. It stated that the different aspects of quantum phenomena, such as the wave and particle natures of light, were not contradictions but complementary truths. Each offered a partial view, and only together did they form a complete picture of reality. This principle became the cornerstone of Bohr's interpretation of quantum mechanics and the guiding philosophy for generations of physicists to come. In the atmosphere of 1920s Europe, Bohr's ideas found fertile ground. The old certainties of classical science had already been shaken by war, technology, and cultural change. Artists were breaking with tradition, philosophers were questioning the foundations of reason, and physicists were discovering that even the smallest parts of nature resisted definitive explanation. Bohr's vision of complementarity seemed to mirror the spirit of the age, a recognition that truth might not lie in absolute statements, but in the harmony of opposites. Copenhagen became the intellectual capital of this new science. At Bohr's institute, physicists gathered from across the world, drawn not only by his genius but by his openness and humanity. Days were spent in intense study, nights in endless discussion. Bohr encouraged his students to challenge him, to argue, to think freely. He believed that understanding emerged from dialogue, not authority. His office became a crossroads of the modern mind, a place where the boundaries between science and philosophy blurred. Visitors often described Bohr's teaching style as both patient and profound. He would listen to a question with complete attention, sometimes in long silence, before replying with another question that led his students to think more deeply. His method reflected the very nature of quantum theory itself, a balance of uncertainty and discovery, of knowing and not knowing. Under his guidance, the young pioneers of quantum mechanics felt they were part of something larger than themselves, something that transcended the confines of ordinary science. Yet not everyone accepted the strange new principles Bohr championed. Einstein, despite his early contributions to quantum theory, grew increasingly skeptical. God does not play dice, he famously remarked, rejecting the idea that the universe operated by chance and probability. To Einstein, the apparent randomness of quantum mechanics was a sign that the theory was incomplete. Bohr responded with characteristic calm and subtlety, saying, "Einstein, stop telling God what to do." Their debates became legendary, not hostile, but deeply respectful. It was as though two great minds were engaged in a philosophical chess match, each move sharpening the understanding of both. As the 1930s, quantum theory was no longer a speculative idea, but a powerful framework that explained a vast range of phenomena, from the spectra of elements to the behavior of electrons in metals. Bohr's interpretation, with its emphasis on complementarity and the role of observation, became the philosophical foundation of this new science. But for Bohr, the work was never just about equations or experiments. He saw quantum theory as a window into the nature of human thought itself, a reminder that our understanding of reality is always shaped by the tools we use to observe it. By then, his institute had become a beacon of hope in a world sliding toward darkness. Political tensions were rising across Europe, but inside those walls, collaboration continued. Physicists of every nationality, speaking different languages, shared one common goal: to understand the quantum world. For Bohr, this unity of purpose was a reflection of the deeper unity of nature that quantum theory revealed, a harmony hidden beneath apparent contradictions. In those years, Bohr's home in Copenhagen became a symbol of intellectual refuge. His family welcomed scientists, philosophers, and students who came seeking not just knowledge but inspiration. The evenings were often filled with quiet conversation and music, with discussions drifting seamlessly from physics to poetry. Bohr's belief that science and art shared the same creative spirit gave those gatherings a timeless quality. To him, both pursuits were expressions of humanity's desire to find meaning in the infinite complexity of existence. As Bohr continued to refine his interpretation, he sensed that the quantum world would forever challenge human certainty. No matter how precise the measurements or powerful the theories, there would always remain an element of mystery. Not because nature was hiding something, but because knowledge itself had limits. He came to see this not as a defeat, but as a form of beauty. The universe, in its deepest structure, invited humility. It asked us to accept ambiguity not as confusion, but as truth in its purest form. And so, through the 1920s and beyond, Niels Bohr became not only a scientist, but a philosopher of uncertainty. A voice reminding humanity that the smallest particles of matter reflect the greatest questions of existence. His introduction of quantum concepts did more than revolutionize physics. It reshaped the way we understand knowledge, reality, and ourselves. The winter skies above Copenhagen were pale and silent, but inside Bohr's institute, the air was alive with thought. Papers lay scattered across long oak tables, their margins filled with penciled equations and sudden bursts of inspiration. Young scientists moved softly through the halls, carrying notebooks like explorers carrying maps of an unseen world. They knew that within those chalk-streaked walls something greater than theory was taking shape, a new way of seeing reality itself. Niels Bohr, calm yet endlessly restless, stood at the heart of it all, guiding, questioning, and shaping the ideas that would forever change science. By the late 1920s, quantum theory had begun to weave itself into every corner of modern physics. The language of quanta was no longer the strange dialect of a few visionaries. It had become the vocabulary of the universe. Bohr watched this transformation with both pride and caution. The equations now worked. They predicted atomic spectra, chemical behavior, and even the glow of distant stars. But beneath the mathematical success, Bohr saw a deeper enigma. What did it all mean? What did the wave of Schrödinger or the matrices of Heisenberg truly represent? Were they pictures of reality or just tools of prediction? To Bohr, the answer lay not in the symbols, but in the relationship between experiment and knowledge. He insisted that the new physics could not be interpreted through the lens of the old. At the quantum level, nature could not be separated from the act of observation. The electron's path, its energy, its very existence in a definite state, all these became meaningful only when measured. Before measurement, they existed as possibilities, overlapping like notes of a symphony not yet played. This idea, both poetic and unsettling, forced science to confront its own boundaries. In 1927, Bohr articulated this understanding formally at the Solvay Conference in Brussels, a legendary gathering where the world's leading physicists met to discuss the strange implications of quantum mechanics. The atmosphere was electric. On one side stood Einstein, defending his belief in an objective, deterministic universe. On the other stood Bohr, serene but unyielding in his defense of complementarity and uncertainty. Their conversations lasted deep into the night, their voices echoing through the marble corridors of the Hotel Métropole. Einstein proposed thought experiments to expose what he saw as the absurdity of quantum indeterminacy. Bohr, thinking carefully, responded to each one with quiet precision, showing how the quantum laws preserved consistency even when common sense failed. By morning, the others looked on in awe. It was not just a scientific debate, but a meeting of worldviews. Faith in certainty against faith in mystery. The outcome was not victory or defeat but understanding. Einstein never accepted Bohr's interpretation fully, yet his challenges helped refine it, giving it sharper form. Bohr later recalled those nights with respect and gratitude. He admired Einstein's insistence on clarity, even as he believed that the quantum world could never be tamed by classical reason. "Every sentence I utter," Bohr once said, "must be understood as a question, not as an answer." To him, the essence of science was not certainty but wonder. Back in Copenhagen, this spirit infused daily life at the Institute. Mornings began with quiet study, afternoons with discussions that blurred into evenings of reflection. The conversations ranged from the mathematics of wave functions to the philosophy of language, from the meaning of causality to the role of consciousness in measurement. Bohr's students came to realize that the quantum revolution was not simply a new chapter in physics, it was a turning point in human thought. The old idea that science could stand apart from the observer was gone. Reality, it seemed, was woven from the threads of interaction. Bohr's concept of complementarity soon found echoes beyond physics. Biologists, psychologists, and even artists began to see parallels in their own fields. The notion that truth might require opposing perspectives to be fully seen. Painters experimented with dual imagery, philosophers spoke of coexistence rather than contradiction, and poets found inspiration in the uncertainty of perception. The influence of quantum thought rippled far beyond laboratories, reshaping how an entire generation understood the act of knowing. Yet Bohr remained modest about these broader implications. When admirers spoke of philosophy, he returned always to experiment. He believed that theory must be anchored in observation, that imagination must serve reality, not replace it. Still, he was aware that quantum theory had forced open a door that would never close. The smallest quanta of energy had revealed that knowledge itself was a fragile, living process, dynamic, relational, incomplete. As the 1930s dawned, new challenges emerged. The discovery of the neutron and the rise of nuclear physics carried the quantum principles into a new realm. Bohr's insights into atomic transitions helped physicists understand the binding of nuclei and the release of enormous energy within them. The mathematics of the quantum, once abstract, now held the key to the power of the atom. Bohr watched this development with both fascination and unease. He saw in the quantum a mirror of creation and destruction, a reminder that knowledge carried responsibility. He continued to refine the philosophical foundations of quantum theory, emphasizing that measurement did not reveal an underlying classical reality, but created meaning within a specific experimental context. There was no single, absolute picture of the world, only different complementary descriptions, each valid within its own frame. This was not relativism, but realism of a deeper kind, one that acknowledged the limits of language and perception. Bohr believed that this humility was essential, not only for science but for civilization. In public lectures, he spoke with gentle conviction about the beauty of uncertainty. The opposite of a truth, he said, is not a lie, but another truth. Those words captured the essence of complementarity. The idea that light could be both wave and particle, that knowledge could be both objective and subjective, that human understanding grew by holding opposites in balance. To his students, these ideas were not abstract philosophy, but the living rhythm of their work. Each experiment, each measurement, became a dialogue with nature, a question asked and answered in the quiet language of probability. Outside the walls of science, however, the world was darkening. Political turmoil spread across Europe, and with it came fear and division. Bohr's institute, once a haven of international collaboration, faced the tension of a continent drifting toward war. Yet even in those uncertain years, the exchange of ideas continued. Scientists from across borders still found refuge in the shared pursuit of truth, carrying with them the spirit of openness Bohr embodied. When war finally came, the quantum world Bohr had helped reveal was turned toward destructive ends. Nuclear fission, born from the very principles he had nurtured, became the basis for the most powerful weapons humanity had ever known. Bohr, forced to flee Nazi-occupied Denmark, escaped to Sweden and later to the United States. There he joined the Manhattan Project, not as a builder of bombs but as a voice of caution. He urged world leaders to think beyond the battlefield, to recognize that the new power demanded international cooperation and transparency. To him, the quantum world's lesson was clear: everything in nature was interconnected, and so too must be humanity. After the war, Bohr returned to Copenhagen, wary but unbroken. He resumed his work at the Institute, which had survived the occupation. There, he continued to explore the philosophical depth of quantum theory, guiding a new generation of physicists. He spoke often about the need for what he called an open world, a world where knowledge flowed freely, where nations shared discoveries for the good of all. In his mind, the complementarity of nature extended to human society. Progress and peace could only exist together. The later years of his life were marked by quiet reflection and enduring curiosity. He corresponded with scholars across disciplines, exploring how the principles of complementarity and uncertainty could illuminate ethics, communication, and human relationships. He believed that just as observation shaped reality in physics, dialogue shaped understanding among people. The act of listening, he said, was the human equivalent of measurement. It defined what was possible to know. In lectures delivered around the world, Bohr returned again and again to the same theme: that the quantum revolution was not simply a change in science, but a change in perspective. It taught that knowledge grows through interaction, that reality is richer than any single description, and that humility is the highest form of wisdom. His words carried the calm authority of someone who had seen the universe from its smallest scale and found in it not chaos but coherence. By the time he passed away in 1962, Bohr's ideas had become the foundation of modern physics. Quantum theory had blossomed into quantum electrodynamics, quantum field theory, and the beginnings of quantum information, each branch tracing its roots back to those early insights about energy quanta and atomic transitions. Yet beyond the mathematics, Bohr's influence endured as a philosophy of inquiry. He had taught that science was not a conquest of nature, but a conversation with it, that every measurement, every theory, was an expression of the human desire to understand. Even today, the principles Bohr helped shape guide technologies that define the modern age, from lasers and semiconductors to quantum computers that manipulate information itself as quanta of possibility. But behind each invention lies the same profound truth, that the universe is not a fixed machine, but a dynamic web of potential, unfolding through interaction. That truth is Bohr's enduring legacy. The story of Niels Bohr and the introduction of quantum theory is not the tale of a single discovery, but of a transformation in human thought. It began with curiosity about the color of heated light and ended with a vision of reality as layered, relational, and mysterious. Bohr's gentle insistence that contradiction could be harmony, that uncertainty could be knowledge, changed not only how scientists work but how humanity thinks about existence itself. And so the camera pans away from Copenhagen, From the quiet rooms where chalk still dusts the air and equations line the walls, the voice of the narrator softens, as if speaking across time. It reminds us that the quantum world is not distant from us. It pulses within every atom of our being. The light that fills our eyes, the charge that runs through our hearts, the patterns that shape our thoughts, all are born of the same invisible rhythm. Bohr devoted his life to understanding. He taught us that reality is not made of certainty but of connection, and that by embracing the unknown, humanity becomes a little closer to the truth. In the quiet aftermath of his atomic discoveries, Niels Bohr found himself surrounded by minds as brilliant as the light that once puzzled him. The corridors of his Copenhagen Institute became a crossroads of genius, a sanctuary where young physicists from every corner of the world gathered to exchange ideas, challenge assumptions, and shape the destiny of science. Here, collaboration was not merely an academic practice, it was a philosophy of life. Bohr believed that the deepest truths could never emerge from solitude, but only from conversation, from the friction of differing thoughts, refining one another like stones in a river. In those years, names that would later fill textbooks passed through his doors: Werner Heisenberg, Wolfgang Pauli, Max Delbruck, and others who carried the torch of the quantum revolution. Each brought a spark of brilliance, but Bohr's presence was the steady flame around which they gathered. He did not dictate ideas. He asked questions, sometimes gently, sometimes relentlessly, forcing his students to think beyond the comfort of their equations. When Heisenberg struggled with the strange mathematics of quantum motion, it was Bohr's patient insight that guided him toward clarity. Their relationship became one of the most fruitful partnerships in science, a dialogue between the intuitive youth and the contemplative mentor. Together, they explored the heart of uncertainty, Heisenberg's principle, which declared that one could never know both the position and momentum of a particle simultaneously, found philosophical grounding in Bohr's idea of complementarity. The two concepts intertwined, forming the intellectual backbone of quantum mechanics. Yet, like all collaborations between great minds, theirs was not without tension. Late-night discussions sometimes turned into debates that stretched into dawn, their voices echoing through the halls of the Institute as they struggled to express the ineffable nature of reality. Bohr's calm persistence balanced Heisenberg's youthful intensity, and from their clash of perspectives emerged a deeper understanding of the quantum world. Bohr's collaboration extended beyond his immediate circle. Across Europe, he engaged in letters and conferences with the titans of theoretical physics. His correspondence with Albert Einstein remains one of the most remarkable dialogues in the history of science, a philosophical duel fought with respect and precision. Einstein, ever the realist, could not accept the idea that chance ruled the universe. His famous protest, "God does not play dice," became the rallying cry of those who sought a deterministic explanation. Bohr, equally determined, replied not with arrogance but with humility. He insisted that the quantum world did not defy reason, it redefined it. To him, the dice were not symbols of chaos but of a deeper order, one that human understanding was only beginning to glimpse. Their exchanges, though often intense, were rooted in mutual admiration. Each pushed the other toward greater depth, proving that disagreement, when guided by respect, can be the most productive form of collaboration. Beyond theory, Bohr's role as a mentor and collaborator carried moral dimensions. When political shadows darkened Europe in the 1930s, he used his influence to protect and support displaced scientists fleeing oppression. His institute became a refuge for thought, an island of intellectual freedom amid the rising tide of totalitarianism. Many who found safety under his guidance later became leaders in their own right, carrying forward the spirit of openness that defined Bohr's philosophy. He saw science as a universal language that transcended borders, and in that belief, his collaborations became acts of humanity as much as of intellect. After the war, Bohr continued to build bridges rather than walls. He advocated for international cooperation in the peaceful use of nuclear energy, warning that the same knowledge that could light cities could also destroy them. His discussions with global leaders, including Churchill and Roosevelt, reflected the same earnestness he had shown in scientific debates. He sought understanding, not victory, communication, not control. To him, collaboration was the only way forward, both in science and in the fragile balance of human civilization. Even in his later years, Bohr's mind remained a meeting ground for ideas. Younger scientists, inspired by his humility and depth, would sit for hours in his study, where chalkboards covered with equations coexisted with quiet pauses of thought. He listened more than he spoke, allowing others to discover insights through their own reasoning. His strength lay not in answers, but in the questions he inspired. In the end, Bohr's collaborations formed an invisible web that spanned decades and disciplines. They were not defined by co-authored papers or shared experiments alone, but by the transformation they brought to those around him. Every mind that worked with Bohr emerged changed, more thoughtful, more precise, more aware of the delicate interplay between knowledge and mystery. Through these relationships, the abstract beauty of quantum theory became a human story, woven from dialogue, debate, and the quiet courage to explore uncertainty together. And as history looks back, it becomes clear that Niels Bohr's true genius was not only in the theories he created, but in the minds he awakened. In his collaborations, he built a living testament to his deepest belief that truth, like light itself, shines brightest when shared. In the later chapters of Niels Bohr's life, his focus shifted from the mysterious depths of the atom to the equally complex landscape of human responsibility, the fifth great theme of his journey. His contributions to nuclear physics and his ethical vision for the atomic age was born from both discovery and dread. Bohr understood that the same quantum principles that had revealed the beauty of the microscopic world also held the key to unimaginable power. The energy locked within the nucleus of the atom, once a theoretical curiosity, had become a living force capable of altering the course of civilization. And as nations raced to harness it, Bohr found himself standing at the intersection of science and conscience. It began quietly in the years before the Second World War, when physicists like Otto Hahn and Lise Meitner uncovered the process of nuclear fission. Bohr recognized at once what it meant. The splitting of uranium nuclei was not just another milestone in physics, it was the dawn of a new era, one that could light the world or burn it. His intuition, honed by decades of contemplating the dual nature of reality, told him that humanity's understanding had outpaced its wisdom. He had always viewed knowledge as a dialogue between humans and nature, but now that dialogue carried a grave warning. The universe had whispered its secrets, and mankind had to decide how to listen. During the war, Bohr was drawn reluctantly into the world of politics and secrecy. As Denmark fell under occupation, he worked quietly to preserve his institute and the lives of those who depended on it. But when the pressure of Nazi control grew unbearable, he was forced to flee, first to Sweden, then across the icy North Sea to England, and eventually to the United States. There, he was brought into contact with the Manhattan Project, the colossal effort to build the first atomic bomb. To many, it was a race for survival. To Bohr, it was a moral test. He joined not as an architect of destruction, but as a messenger of caution, urging those around him to see beyond victory to the consequences that would follow. Bohr's conversations with American and British leaders during that time carried a quiet urgency. He spoke of what he called an open world, a vision in which scientific knowledge would be shared internationally to prevent the secrecy and rivalry that had fueled war. To him, the atomic bomb symbolized not triumph but tragedy, a proof that humanity had entered a new stage of existence without yet learning how to live in it. He believed that transparency and cooperation were the only antidotes to fear. His proposal was both idealistic and pragmatic. Only by building trust among nations could the same science that split the atom help unite the world. When Hiroshima and Nagasaki were destroyed, Bohr's fears became reality. The brilliance that had begun as pure inquiry had culminated in fire. For Bohr, it was a moment of profound sorrow. Yet even then, he refused to turn away from the responsibility that knowledge demanded. Returning to Copenhagen after the war, he dedicated himself to promoting the peaceful use of atomic energy. He wrote open letters to the United Nations and world governments, warning that nuclear weapons would make isolation impossible, and that the fate of civilization now depended on dialogue. His voice, calm and reasoned, became a moral compass in an age trembling with power. In the years that followed, Bohr continued to contribute to nuclear research, but his work took on a new character, one of reflection and restraint. He helped establish international frameworks for atomic collaboration, emphasizing that the progress of science must serve humanity, not threaten it. Younger physicists who visited him in those years often found him less interested in equations and more in ethics. He spoke of complementarity not just in physics but in life, the idea that reason and compassion, logic and morality, must coexist if humanity was to survive its own genius. To many who met him, Bohr's presence carried the same quiet strength as his theories. He did not preach, he conversed. He believed that understanding could only emerge through dialogue, just as the truth of quantum nature revealed itself only through interaction. In the same way, he saw world peace as a quantum relationship, a balance between nations that could only exist through openness and trust. His scientific philosophy and his ethical vision were, in the end, inseparable. In his final years, Bohr's thoughts returned often to the young scientists who had once filled his institute with laughter and argument. He worried about the burden of discovery they would inherit. Yet he remained hopeful. He believed that curiosity, when guided by humility, was still the noblest force in humanity. His dream was not of power but of understanding, a world in which the energy of the atom would illuminate minds rather than destroy lives. When Niels Bohr died in 1962, the nuclear age was still young and the world still uncertain. But his legacy endured, not only in the laboratories that carried forward his work, but in the conscience of science itself. He had shown that knowledge without wisdom was dangerous, but knowledge guided by humanity could be divine. In every reactor that lights a city, and in every scientist who questions how their discoveries should be used, Bohr's spirit lingers. He stands as a reminder that the greatest discovery of all is not the atom or the quantum, but the moral courage to use them wisely. In the calm twilight of his years, Niels Bohr turned his gaze inward, reflecting not just on the atoms and theories that had defined his life, but on the deeper meaning of knowledge itself. The sixth great theme of his journey, his influence on modern physics, and the continuing evolution of his ideas, stands as one of the most profound legacies in the history of science. To understand Bohr's impact is to follow the invisible thread that connects his quiet thoughts in Copenhagen to the most advanced laboratories and quantum computers of the 21st century. His theories, once scrawled in chalk on the walls of his institute, have become the foundation stones of a new technological civilization. In the decades after his death, Bohr's interpretation of quantum mechanics continued to shape every major breakthrough in physics. The concept of complementarity, his belief that light and matter could behave as both waves and particles depending on how they were observed, became not just a scientific idea but a philosophical compass. It guided generations of physicists in their attempt to make sense of a universe that seemed to defy logic. When scientists studied the behavior of electrons, photons, and even entire molecules, they found again and again that Bohr's principle held true. Reality was not fixed but conditional, defined by interaction. The observer and the observed were part of the same dance, inseparable in the act of measurement. As quantum theory deepened, new fields arose: quantum electrodynamics, quantum field theory, and later, quantum information science, all echoing the language of Bohr's thought. The strange superpositions and uncertainties that once puzzled his contemporaries became the essential tools of modern physics. Even as equations grew more complex and experiments more precise, Bohr's voice lingered in the background, reminding scientists that understanding required humility. His insistence that science must recognize its limits, that nature could never be fully captured by human logic, proved to be not a weakness but a strength. It allowed physics to grow flexible, adaptable, and open to the unknown. The influence of Bohr's ideas extended far beyond the boundaries of science. Philosophers, psychologists, and even artists drew inspiration from his vision of reality as relational and dynamic. The idea that opposites could coexist, that contradictions were not flaws but features of existence, resonated deeply in a world struggling to make sense of complexity. In literature, metaphors of quantum uncertainty appeared to describe human emotion and thought. In art, painters experimented with dual perspectives, capturing the tension between objectivity and perception. And in philosophy, thinkers such as Karl Popper and Thomas Kuhn grappled with the implications of Bohr's views on knowledge, that truth was not absolute but dependent on context. Meanwhile, in laboratories across the world, new technologies began to emerge that turned Bohr's abstract concepts into physical reality. The transistor, the laser, the semiconductor chip, each of these inventions, in some way, owed its existence to the understanding of quantum principles Bohr helped pioneer. Decades later, when the idea of quantum computing took shape, scientists once again invoked his legacy, a machine that could exploit superposition and entanglement, the very phenomena that Bohr and his students once debated by candlelight, now promised to revolutionize communication, cryptography, and artificial intelligence. It was as if the old chalkboards of Copenhagen had come to life, their equations breathing power into the modern world. Yet, for all his scientific influence, Bohr's deeper gift lay in his way of thinking. He taught that science was not a battle for certainty, but a dialogue with mystery. His calm, reflective manner shaped the culture of physics long after his passing. Young researchers learned from his example that progress came not from arrogance but from openness. He showed that true genius was not in claiming to know, but in daring to ask. His famous words, that the opposite of a truth is not a lie, but another truth, became a guiding principle for thinkers in every field, a reminder that reality was richer than any single perspective could grasp. As the 20th century drew to a close, Bohr's name appeared in textbooks, lecture halls, and Nobel citations, often side by side with those of his students. Werner Heisenberg, Wolfgang Pauli, Max Delbruck and others carried his spirit forward, expanding his insights into new realms of physics and biology. Their work, in turn, inspired future generations. From Richard Feynman's playful genius to the visionaries of the quantum age, who now probe the universe with tools Bohr could only dream of. Each discovery, each equation, seemed to whisper the same message he had taught in Copenhagen, that knowledge is an unfolding process, not a final destination. Today, the echoes of Bohr's philosophy reach far beyond laboratories. They touch the ethical and existential questions of our age, questions about artificial intelligence, the nature of consciousness, and the limits of human understanding. His belief in complementarity, the harmony between opposites, offers a model for coexistence in a divided world. Just as light can be both wave and particle, humanity can be both rational and emotional, logical and compassionate. Bohr's insights remind us that balance, not dominance, is the true path to progress. In the end, Niels Bohr's influence cannot be measured only in the language of science. It lives in the way humanity now sees itself, as part of a universe both knowable and mysterious, precise yet unpredictable, grounded in mathematics yet shimmering with possibility. He transformed physics into a mirror of the human condition, showing that our search for truth is not a conquest but a collaboration. And as quantum theory continues to expand, touching every corner of technology and thought, Bohr's presence remains quietly luminous, like the glow of a single atom seen through the darkness, a reminder that the smallest truths can reveal the vastness of existence itself. In the final movement of Niels Bohr's story, the focus turns from discovery to legacy. From the man who unveiled the secrets of the atom to the philosopher who redefined humanity's relationship with knowledge. The seventh and last great theme of his life was not found in equations or experiments, but in the enduring power of his ideas to guide generations long after his death. Bohr's influence did not end with the quantum revolution. It continued to echo through the corridors of science, philosophy, and culture, shaping how people think about reality, truth, and themselves. As the decades passed, Bohr's quiet wisdom became a compass for those seeking meaning in an increasingly complex world. His principle of complementarity, which once explained the paradoxical nature of light and matter, grew into a universal philosophy. It taught that opposing truths could coexist, that understanding required balance rather than certainty. To scientists, it was a rule of physics. To thinkers and leaders, it became a lesson in life. Bohr's gentle reminder that every great truth is one whose opposite is also a truth resonated far beyond laboratories. It found a place in discussions about ethics, politics, and even human relationships, wherever people struggled to reconcile conflict and find harmony in contradiction. Within the scientific world, Bohr's legacy remained deeply personal. The institute he founded in Copenhagen continued to thrive, a living monument to his belief in collaboration and open inquiry. Scholars from every continent came to study there, drawn by the same spirit of curiosity and humility that had defined its creator. The walls that once echoed with debates between Bohr, Heisenberg, and Pauli now carried the voices of new generations probing deeper into the mysteries of the quantum world. They built on his foundation, exploring phenomena he could only imagine: quantum entanglement, teleportation, the structure of subatomic particles, and the nature of information itself. Each breakthrough seemed to confirm that Bohr's vision of an interconnected universe was not just philosophy, but reality written in the language of physics. Outside academia, his name became a symbol of integrity and responsibility in science. During a century when technology advanced faster than morality, Bohr's life offered a reminder that knowledge must be guided by ethics. His warnings about the dangers of nuclear weapons and his call for global openness remain relevant in every age of uncertainty. Policymakers, historians, and peace advocates have often returned to his words as they grapple with how to use power without losing humanity. Bohr believed that the same principles governing quantum particles, interaction, dependence, and balance, applied equally to nations and individuals. Only through communication and mutual understanding, he said, could the world remain stable in the face of boundless potential. Even beyond the realm of science and policy, Bohr's thought left an imprint on how people perceive the nature of reality itself. The idea that observation affects outcome, that the observer is part of the event, entered psychology, art, and literature. Writers began to explore the idea that perception shapes existence. Artists captured the fluid boundaries between subject and object. Philosophers debated whether consciousness could ever be separated from the world it observes. In this way, Bohr's work bridged the gap between physics and human experience, reminding us that the smallest particle and the largest thought are threads of the same cosmic fabric. In classrooms around the world, his story continues to inspire. Students who first encounter the strange beauty of quantum mechanics often find themselves drawn not only to its equations, but to the questions it raises. Questions Bohr himself loved to ask. What is reality when observation changes it? How do we define truth in a world of probabilities? What is the role of the human mind in the unfolding of nature? For Bohr, these were not puzzles to be solved but doors to be opened. His legacy endures in the spirit of wonder that drives young scientists to look beyond what is known and to embrace uncertainty as the beginning of understanding. In his later years, Bohr once said that the purpose of science was not to eliminate mystery, but to deepen it. He believed that the more humanity learned about the universe, the more profound its questions would become. This humility, the acceptance that knowledge is never complete, may be his greatest gift to the modern age. In a time when technology promises control and certainty, Bohr's philosophy reminds us that true wisdom lies in recognizing limits, in seeing complexity not as a barrier but as beauty. Today, his name stands alongside the greatest thinkers in history, Newton, Einstein, Planck. Yet Bohr's uniqueness lies in the humanity that infused his science. He was not only a physicist, but a poet of thought, a man who saw in the atom a reflection of life's contradictions. The laboratories of today, filled with quantum computers and particle accelerators, still carry the imprint of his curiosity. But beyond machines and mathematics, his legacy lives in the idea that truth is relational, that understanding grows through dialogue, and that the universe itself is an ongoing conversation. As the years roll on and the quantum age unfolds into new dimensions of technology and thought, Niels Bohr remains a silent guide, a steady light within the storm of discovery. His voice, soft but enduring, seems to whisper through time that to seek knowledge is to seek connection, that uncertainty is not chaos but possibility, and that within every mystery lies the promise of meaning. And so, his legacy continues, not as an echo fading into history, but as a living rhythm in the heart of science and the soul of humanity.